16 different samples. So you probably go all of it. Then you stain it, and then you count it. Now, knowing the volume that you put on it, and knowing the area that you're counting them in, you can calculate the number of bacteria per volume, or per cubic volume, whatever your unit you want. That's a direct count. You're directly counting. You're staining them, you're counting them, you're looking at it. Just like you do with the hemocytometry, or the petrocalcimetry. Just as we saw in the there are some very sophisticated ways of doing it. And one of the more common ways involves what we call particle counting. And you may know this as Coulter counting. Coulter was the first company that made these particle counters. So it's a little bit like the Xerox machine. How many of you use the term Xerox as a verb when you're copying notes or copying something? We call it Xerox that. Well, really, you're photocopying. We call it Xerox because Xerox was the first photocopier of an envelope. Now, there's many others, but even if you're using a Sharpie, probably still on those Xerox. Well, the first company that made these particle counters were called Coulter. Picture of it right there. The Coulter counter. The particle counter. This is a Coulter brand particle counter. But in essence, this is how it works. Setting in here, there is a long, thin, very thin capillary tube. Now, I know you know what a capillary tube is, but we're talking something about a tenth that size. And what you do is you take your sample, typically it's no more than maybe a milliliter. It's got cells in it, and you place it into that tube. Now, that tube also has imposed across it an electrical charge. So when particles pass through that charge, they interrupt it. And when they interrupt that charge, it's advanced on the counter. So you can count up to, well, I can count blood cells. With a particle counter, I can count up to 40,000 cells in about 15 seconds. And it's really very active. So you can set standards, and it's very active. The nice thing about this is that you can set windows. You can set what's called a gate. So that if I've got a mixture of, let's say, Lactis and Saccharomyces cerevisiae. Remember, Saccharomyces cerevisiae had no yeast, very big cell. It's off the first thing we have, if I remember. And then Streptococcus or Staphylococcus, they're very small, 1 micrometer. So I can say, okay, count only those cells that are less than 2 micrometers in diameter, and we'll count only those, disregarding those that are larger. Or I'm going to count only those cells that are larger than 10. The Saccharomyces is about 8 to 20, so I'll count all those, and disregarding bacteria. So very nice, particle counter. Very rapid, very active, but there is an inherent problem with all of these. That problem is that you're measuring total numbers of cells, and you may want to know viable numbers. How many of those are living? If you're going to set up an assay, if you're going to inoculate a place, you want living cells. If they're all dead, that's not going to be very good. So how can we determine viable cells? Well, your book mentioned it, so I'm going to show you a couple slides. But it mentions a flow cytometer. A flow cytometer. The solution is to use a flow cytometer. This is what one looks like. The term flow cytometry and fluorescence activated cell sorter are almost synonyms. So you may see FACS as a flow cytometer. FACS is an acronym for fluorescence activated cell sorter. It's a cell counter in this minimalist setup. It will sort cells for you. This is what it looks like. About $280,000. The software for it alone is 10 grand. So you're not going to find this everywhere. But this is very useful when you're analyzing cell populations, particularly if you're looking at bacteria and the viable ones. To give you an idea of some of the things that we get different plots. This is a plot showing you living cells versus dead cells. This is called scattergram. These are living cells, these are dead cells. And it will count these cells. And it will actually sort and separate these cells from these other cells. Hence the term, fluorescence activated cell sorter. Get all sorts of data from this. You see these types of plots in literature, you'll know what it is. Okay. So, we have particle counters, we have reads here, there's some microscope size of those counters here, or we have a boundary shape. We're measuring we're counting cells, but viable cell count depends on viable assays. That's why we need to count some aspect of the living, and that's typically what we're going to be doing in the lab what's called a standard plate count. Standard plate count. This is maybe we can come back, although it's been our experience that we would come back to maybe we're physically, but respiratory is typically about a week or so. We may be waiting. I don't know. But anyway, we're going to standard plate count at some point. And this is the gist of it. You're going to take your sample, it will be probably an equal line or a rock. And we're going to make serial dilutions. Now here we're making serial tenfold dilution. We take 1 ml from our sample, we add 9 ml of rock, and then 1 in dilution. Take 1 ml of that to the next tube, 1 to 100. Again, you're going to be making serial 100-fold. But at some point, we will take out of these tubes, we'll take out an aliquot, and we'll plate it onto medium, and we'll allow the cells to grow. And then we'll come back after incubation, we'll count the number of colonies that result from those cells that we plated. And then we'll end up with a number, do a calculation, the number of bacteria per milliliter. It's a viability assay. It's a direct cell count. Another one, I wish you would have left it out, but because it does include, I feel, a most probable number. This is an assay that measures viability. It is used, the only place I know it is used is in water quality measures. I used to be a consultant for Carmel, a water system. They did MD and not a lot of people. I began to try to use some less. But anyway, it is a statistical count. We do not actually count bacteria the way we count when we get with viral hypothesis. And what you do is you make dilutions. Your book is right. Your book describes it to a group. But it's difficult to understand if you don't know what you're talking about. So this is water sample. Take your sample, and you make dilutions. And then you plate those dilutions. You'll plant 1 ml into a series of 3 tubes or 5 tubes of different dilution. And then you incubate. And then you wait to see how many of those tubes that each dilution shows weight. Then you count the number of tubes, and you might have 4 breeding tubes. And you compare that to a chart. It's relatively accurate for water samples. It's certainly not something you can find in a clinical laboratory. But SPM is a means of measuring viable numbers of bacteria. Another one is called membrane filtration sample. This is really nice. Let's show you how it looks like. This is the setup. Here we have a flask that has a side on to it that's like it hooked to a vacuum. And here we have a reservoir that down here we have a filter. Now this is used, this type of apparatus is used if we have what to count the number of bacteria in a very dilute preparation. All right? This is one of those apparatus. Typically what you do is this. I'm going to place membrane
very, very thin. I'm going to speed this up. You never want to touch it. That's our filter paper. These are nitrocellular. Sometimes they're even made out of plastic, but while you can't see it, if you put this on a microscope, you see that this is just loaded with pores, little holes that are of a uniform size. Now these happen to be 1.2 micrometers in size. In other words, anything smaller than 1.2 micrometers is going to pass right through them. Anything larger will be retained on the filter. So what we want to do, we have to do this aseptically, so this comes off of it like this. Filter on there. Put the reservoir on here. Wrap it together. The lid that goes on here, we wrap this. Actually, wrap the whole thing with paper and put the water and sterilize. You don't put the water and you don't put it in. So you sterilize this. Now, while you're doing that, your colleague is going down here to White River Canal. They're collecting 100 milliliters of canal water. All right. So they bring it up here, and they want to do it aseptically. I mean, you want a sterile container. You don't want to take a container down here that has bacteria in it. A sterile one, like 100 mil, bring it back. Now, what we do is we set this up, hook this up to a vacuum, just like you see there. The vacuum is going to cause any fluid to be pulled through. Pour 100 mils in there, up to run through, and then we take it apart. Again, aseptically, we take our filter, which now contains any bacteria that's larger than 1.2 micrometers. E. coli is 3 to 4. So beyond there. Let's suppose we look at the E. coli in the canal. E. coli is the fecal indicator of water pollution. So you now take that, and I got a little petri dish here. I can put a selective medium in it. One doesn't encourage the growth of E. coli, it encourages the growth of everything else. So I take it, I put it in here. I incubate this plate. And then 24 to 48 hours, I come back and I count the number of colonies growing on that little piece of paper. That would be the number of E. coli per 100 mil. If I wanted to count for Listeria, I got a selective medium for Listeria. All that one lab knows about selective and differential medium. We all have labs that accept the You're going to learn about selective medium. That's a medium that will encourage the growth of one particular organism. In this case, E. coli. Okay. Again, if you have a bacterial number that are low numbers, we would not expect 10 to the 6th bacteria or even E. coli. Most bacteria that E. coli is a bacteria in these smells. We trap the bacterial cells on the filter. Now, clearly, you have to have a pore size that is smaller than the organism you're trying to enumerate.